Good morning, everyone. Oh, that lighting did not work. I was trying to shed a little bit of light on the oscilloscope because it's in a kind of an area that doesn't get a lot of light when I'm streaming, and then I realized the light I turned on it was way too bright. So I'm just adjusting that there. Is that any better? Yeah, I just don't think we need it. I think we'll just deal with it like that. How you doing? It's my last day of vacation. Tomorrow I gotta go back to writing code for other people. So that means today, as much as I can, I'm gonna try and write as much code as I can for me. Get this board doing some interesting stuff. So where did we get to last night? Well, I think if I remember correctly, I was pretty late, but I did start writing at least some documentation around. Start writing some documentation, I think, here around the way we're going to do the I2C messages between the rotary PIC, the ROT PIC, and the main microprocessor, the STM32. Yeah, I did. Cool. Let's see. Where's the darker preview? That's better. Okay, so when we transmit a byte to the rotary PIC, it has up to, I spec'd it out so it could have up to 6 LEDs on it. I think in reality we only use 4 of those at the moment, but the potential is there. So that's what we're transmitting, and this is LED 1 on off. We should be just clear about the fact that it's a binary on and off. And then when we receive from rotary PIC, this is the real interesting stuff. This is when we start to get back the state of the where we start to get back the state of the oh, I can't think straight. The knobs, the control knobs. That's what this whole thing is for, right? Oh, brain's not working. Okay, and in this case, rather than being a byte, we're going to describe the whole byte coming back. And this is going to be, so it's an int 8t. Actually, let's just do a signed 8-bit int. And then we'll call it rotary encoder 1 delta, right? Because what this does is, I'm gonna bucket up the table here, hang on. We essentially are going to return bytes that indicate the how much the rotary encoder has moved, right? Because remember, these knobs can just be turned infinitely; they just spin around and around. And what we need to be able to do is, when one of them is moved, that's got to send a signal to the main processor to say, "Hey, you need to read the value on these. Something's changed." But then it needs to say, okay, well, what's changed? And that's what we're saying here, is we're saying that when we receive bytes back from the rotary PIC, the first byte is the encoder 1 delta. So has it moved up or down? Up being, I guess, clockwise movement, down being counterclockwise. We can finesse that later. But then so that's going to be, there's essentially going to be 1, 2, 3, 4 of these. So data byte 0, 1, 2, 3, and it is going to be rotary encoder 2, rotary encoder 3, rotary encoder 4. There's a couple of other things that this does. Not only do we need to send back the delta of each rotary encoder, we need some way to describe the switch states, because let's take a look at the schematic. The rotary encoders come in a couple of different forms, and the most notable difference that we're talking about here is that some of them have an inbuilt push button switch, so not only can you turn it, but you can push it in as well, which is quite handy if you're having like multiple functions on one single control knob. So see here, this one has a switch, whereas this one doesn't. And I spec'd out, well, I designed, spec'd out, I don't know what you want to call it, spec'd out the PIC such that I think I support up to 2 switches here. So there can be switch 1 and switch 2, because sometimes, like here, in this set of 4 encoders, 2 of them have a switch, 2 of them do not. So we're going to need a couple of bits here to describe that. Let's go back here. So we've got the 4 bytes that are the state of the rotary encoders. Now let's add a 5th byte, byte 4, which is going to be a so we'll just call this bit mask, and what it's going to describe is the switch states. Okay, so then we'll need to describe that switch state and we'll use a similar table to what we did here. So we've got 8 bits to play with. Now a switch can either be you know, on or off, right? Pressed or not pressed. But I think, what should we do here? We've got to indicate not only the current state, but whether or not it's changed. I think. Which we can do because, you know, we get an interrupt on change. So I think, yeah, I think it's down to us to say, here's the state, and it has changed. So why don't we see what that looks like? So bit 0 would be switch 1 state. On off, and switch 1 has changed. Do we need to do that? Yeah, we do, because if it's a momentary switch, it may well be back to the off state, but you want to know that it had changed. Yeah. Okay, so let's just do this anyway. We've got the data, so we'll do it. Okay, so that's going to be basically our format. We've got 2 switches to play with. So then bits 2 and bits 3 will be switched to state. So is the switch on, is the switch off? And then bit 3 is the did change. So have we actually seen a material state change here? Why is this centering like that? I don't like it. I'm guessing, is it that? Yeah, okay. Let's fix that here as well. Still getting my head wrapped around the intricacies of tables in Markdown, but I really like it. I like working in Markdown. It's quite good. Alrighty, so that's the switch state bits. And then we then have a bunch of bits that are not used because we don't have 4, 5, 6, 7. 4, 5, 6, and 7 bits are unused. Okay, so we need to add in, we need to fix up formatting a little bit here. Receive, why is that? Why is there no gap there? I want there to be a gap. Like I said, still learning Markdown. I'd really like that to just be a sort of a gap like there is between those headers there. So I squared C, right. Transmit to the rotary PIC. When we're transmitting to the PIC, we've got 6 bits to set the LED on or off. When we receive data from the PIC, we get 5 bytes back from it. First 4 bytes describe the state of the rotary encoders, how much have they changed since we last read. And then we also read back the switch state bits. Now, one of the things that's going to be important here is just to note the status that all values. Well, let's note all rotary encoder values.
May I have your attention, please? A false alarm has been detected. The all clear is now given. Thank you for your patience and understanding.
Great. So the fire alarm that was before has now been declared false alarm.
Attention please. Testing of the fire alarm system is now complete.
That's great.
Please treat all further alarms as normal and follow normal evacuation procedures.
I've never lived in a building that tests its fire system as much as this does. And honestly, the people that come out here and test the fire alarms, they're absolute idiots. I caught them at the fire panel one day using FaceTime with each other to work out how to make the panel work. And then they ended up setting off 5 different fire alarms without giving any residents any notice. So, a scathing letter was written to the building management, of which of course had zero effect, as most scathing letters do. But yeah, I really dislike the fire management people here. Anyway, sorry, tangent. So all rotary encoder values are reset to 0 after being read. Right, so you get one shot at this. We are a super simple 8-bit microprocessor. We're not maintaining state for you, we're not tracking stuff for you. If you read these values, you read the deltas, that's it, they're back to 0, and you've got to read it again to work out how far it's moved since then. Likewise, switch state values, switch state on-off values are read directly from the current state of the pin. The did change state is reset after being read, right? So same sort of thing. You get one shot at this. After you've read that state, I'm going to obliterate that. And you're going to have to come back later and ask me again if you want anything else. What else? I don't really... Can we just... Ah, that's better. Italics is much nicer. There we go. Well, I think we're ready to write some code. Yeah, I think we've monkeyed around enough here with documenting stuff just so we don't forget in the future how this works. What should we do first? Let's do the LEDs. That's a nice easy one, right? Now, how will we do that? So, let's first of all get rid of our breakpoints. And I think I started just mucking around with this a little bit here. Oh, I did. Look, I actually did start writing this. That's right. So these we've got our new RX callback and our TX callback, and we wrote our own little I2C in it after all the kerfuffle of trying to get this to work with the boilerplate code. And what I added in was an RX index and a TX index and an RX command. But I'm actually going to, I think I'm going to get rid of that. We don't have the notion of a command. We only have an index, right? We just need to know which byte is this, or which byte are we reading, which byte are we writing. I don't know what we're doing. But what we can do is just know that if we're at RX index 0, that is where this is the first byte that is hitting us, then process it with our I2C RX LED command. And that's it, you know, that could actually, that can be a switch. RX index, case 0. If we're at case 0, no Siri, not you. How on earth you got case 0 out of that? I don't know. Case 0, case, yeah, okay, I see. So if we're at index 0, this is the first byte we've received. We treat it as our command to turn on our LEDs. And then we go and up our RX index. And then when a new address, when we see our own address on the bus again, as in we're starting a new communication with the microprocessor, we go and reset our state. We read the address and we say, okay, we know we're being talked to by someone new. Let's pull, let's reset our index, and our RX and our TX index, knowing that we're about to get something new. Now the TX, all that's doing is just sending back the incrementing index at the moment, so we haven't dealt with that at the moment. But this should be enough. This should be enough to start turning on LEDs around these control knobs based on a command from the microprocessor. And that's a pretty good spot to get to. Let's upload. What's going on here? Hang on a sec, I haven't turned the USB hub on that has the programmers. Woo. Yeah, that's going to make them not work. Okay. There we go. It's found our programmer. Let's upload this code. And we should see no lights on when the code first runs. And we are programming. Aha! Now we should see no lights. And that's 2. Now that would be because we are actually sending. I'm pretty sure this is actually sending some bits to it, so maybe that's to be expected, or maybe not. Let's see. Is it to be expected? Are we actually hitting this? No. Okay. So something else is wrong. What we should do here is just double check the state of the pins and how we've configured them, because Cat wants to come in. If you have caught earlier streams on this project, of which there are many, I made a little bit of it. No, we made a mistake. That's right. Remember when it's a mistake, we made it. We made a mistake where the way that we do the LEDs on the actual LED controllers, like the actual constant current fancy RGB LED drivers, they sync the current because that's how they provide a good, stable, consistent, constant current supply. And I set the LEDs up the same on the PICs as well, which means we're supplying voltage to the LED at all times, but then it's whether or not there is then a connection to ground or not, through which that current can be sunk as to whether or not the LED turns on. But that's not exactly how the PIC. I mean, it can do that. It can sync the current just fine, but it's more designed to actually source the current itself. So I should have done them the other way around, but we didn't. But that's okay. There's just a couple of little things we need to do to work around that. And in particular, if we look at the pins here, the ones that we're using for LEDs, you see we've got LED 1, 2, 3, 4, 5, 6 here in the table. They need to start high, because high is actually no connection. And they need to be set to being an open drain, because that basically says don't try and source any current for this pin, because that's pointless. It's already getting current sourced to the anode of the LED, and current being sourced to the cathode of the LED is just going to do nothing. So we may as well turn that off and just say this acts as an open drain, right? When we drop to 0, when we go to low on these pins, just let the current sink to ground. And so that creates a little bit of an inversion where, in fact, the pin being low goes to ground, which enables the LED to turn on. It's a little bit backwards. That's why we start high, just to make sure that they're not on by default. Oops, I should have generated that config first. Let's do that first. So config's generated. We've got no warnings, I don't think. I kind of did things in a bit of a arse about state here. So just real quick, I'm going to go back and regenerate that config. Okay, it's happy it's generated it, and I'm going to rerun the LED command here. And I did actually see that breakpoint hit, so I think we're definitely sending a data. That's what we do. And by the looks of it, part of that data is sending not the first bit, but the second bit is set to 1. So yeah, that would turn an LED on, which is great. And yes, look, it's hit that breakpoint. So it's hit this breakpoint because it's seeing a byte come in that it thinks should be turning on the LEDs, and it does indeed show a 0x2, which is that binary value being set. The question is, why is it turning on? Why is it turning on two LEDs or multiple LEDs? If we go to the header here, where have I defined this? LED state. Source files. Oh yes, kitty cat. I will let you in just a second. I2CH. Okay, so LED state 1 or LED 1 state. We're looking for a 1 that's been shifted 0, 1 that's been shifted 1, 1 that's been shifted 2. Yeah, that makes sense. So let's step through these one by one, So the first LED comes on, which is wrong. Oh, no, it's not. This is the inversion I was talking about. High is low, low is high. Ah, okay. So what do we do here? Let's just fix these. Each of these should actually be low, because setting it low turns the LED on. So if we fix this in a future revision of the board, then we'll have to adjust this firmware as well. So let's make a comment on that. So we set this high. Okay, and just note, because the LED pins are operating as a open drain current sink, low is LED on, high is LED off. Okay, well that makes more sense now. So now we should only see that one LED turn on when we receive that byte. Okay, we're at the breakpoint. Let's see, let's step through it. So the first bit does no LED on. Second bit, this should turn one on, and it does. This should not turn one on, not on, not on, not on. Yeah, that's it, folks. We have done it. We have one LED turned on based on the microprocessor sending this byte to the little programmable integrated circuit. That's awesome. Stuff's working today. Knock on wood. Give me a sec. I'm going to let the cat in before he gets real cranky with me. So, be right back. I think he gets all weirded out by the fire alarms as well. He's walked in doing his get down low and creep in kind of act. Okay, so that's good. And that keeps getting that byte sent to it. So we just let it happily do its thing. So that's, well, that's this end of the equation handled. We've got the ability to receive a byte and turn our LEDs on as a result. Cool. Now we need to get down to the really interesting stuff. How do we deal with a little twiddle of the knob over on that board actually doing something here that we can, you know, represent that the state of that control back to the microprocessor, back to the big brain. So let's check our code in. That's what we should do first. Let's close all our files, fix our claustrophobia. Files, save, they're all saved. Likewise over here on the MCU, the STM32, let's save that. I think they're all saved. Yep, they're all saved. All right, let's check this in because this huge milestone. Let's do pick LED. Able to control pick LEDs via I2C. Woo! Go us! Alright, but now we start to do something really exciting. Which is the first thing we've got to do is we need some code to run every time one of these knobs is turned clockwise or counterclockwise, left or right. Now, the way that we do that is these have already got interrupts enabled, which is good. One thing I know I'm going to need here is a timer, just a relatively low frequency timer, but a timer nonetheless that I can use as to do things like debounce and other stuff. So I need basically a clock source. So Fosc over 4. And so that's going to give me a... Oh, that's pretty cool. That's basically going to give me a 1 millisecond clock. I like that. Do I need synchronization? Let's turn that off. Enable timer interrupt. That's what I do need. And yeah, let's try that. Got any warnings? Request a time period of 2.56. Yeah, then that's fine. I don't want that. I actually want bang on 1 millisecond. Can I have that? I can have that. Cool. So why is this important? This gives us a callback. So our interrupt handler, you know, we've got a piece of code that is guaranteed to be called every millisecond. Now we've got to be super fast in that bit of code. We can't do anything that would take a long time because otherwise the interrupts will cascade and will pile up. But it's enough to just increment an internal value. Okay, so think of it this way, right? The knobs on these things, because they've got inside them, they've got that wheel of like contact and non-contact pieces. Remember we talked about how the rotary encoders work. They can get a bit jittery, right? So sometimes you're holding onto the knob and you're just trying to smoothly move it in one direction, but you know, your hands jiggle and there's, you know, maybe even interference on the board or whatever. Sometimes it looks as though you've changed direction when you didn't actually mean to. So we do this thing called debounce, where we say if we see a change in direction, but then you know, don't see any actual movement in that direction in a certain period of time, then we just treat that as an anomaly, right? We debounce it. We say that's just bouncing around. It's debouncing. It's bouncing from one direction to the other. Likewise with button presses, right? You don't, if you press a button, what's to say that as you're incrementally applying that force, you don't accidentally make the contact happen like 4 or 5 times really fast, right? So you debounce that as well, right? And then again, physically the contact is bouncing. So you debounce it by having this clock that's running. And you can say, well, hang on, we've seen that switch fire within the last 3 cycles of that clock. So that's 2 presses within 3 milliseconds. No human's done that. That's just a bounce. So ignore it. Right? And that's why we need this. So we're going to go generate our code, and I'll show you how we can then make use of this. Okay, that's generated the code. Now let's go back to the projects here. And if we look at we should now have an extra file here, timer0.c. Cool. And this is the initialization that's set up based on what we've just configured in MCC. But here's the important bit. Timer0 set interrupt handler, timer0 default interrupt handler. So what does that do? Add your timer0 interrupt custom code here or set custom function using set interrupt handler. Well, I would prefer to set my own interrupt handler, please. Excuse me. So I'm going to grab that code and I'm going to create, seeing as we're going to start working on the encoders, let's create us a new file, new C source file, and let's call it encoder.c. Now we're just going to sketch this out a little bit. We're going to have to include encoder.h. We're going to need our own header for this, so let's make one. New header, encoder.h. And I like to set the standard of all my files have an init method that you're expected to call from main in the firmware. So we're going to have encoder. Why did that indent? Oh, what is this thing doing? Why are you indenting? Weird. Alright, let's have void encoder init. Okay. Yeah. Why? I don't know what that's doing. So we're going to have a function called encoder init, and let's write that. What I want this to do is I want it to go and call the timer 0 set interrupt handler, and we're going to pass it a pointer to our function. And we're going to call this encoder clock interrupt, or encoder clock ISR. And I like to start my functions that are internal to the file with an underbar, just an old habit. Just very quickly see, oh, this is internal versus something that we're exposing out to the other rest of the code. So this is our clock ISR. That's our monotonic ping, ping, ping every millisecond. And what we're going to do is we're going to basically just have a uint8t debounce. Yeah, let's just call it debounce. Let's just call two brothers. And all the clock function does is it just increments debounce. And we'll start debounce off at 0 just for fun. Actually, no. Let's just do this. Don't know why this matters to me, but it does. We're going to do debounce equals 0 in the init code. Now, to find this method, timer 0, we need to include the MCC generated files, which we can do by just using this handy dandy MCC generated files import include. And we timer 0 set interrupt handler passing in the clock ISR, and I just want to confirm that we're doing the right thing here. Oops, no, that's timer 0 default interrupt handler. Of course, so we don't pass a pointer to the function, we just pass the function itself, which will be, you know, in the quirky ways that C works. That'll just work. What this means, and we'll test it in just a second, is that we should be seeing, regardless of anything else happening on the board, every millisecond this bit of code runs, which will help us do those debounces. Alrighty, and I'm just trying to think, do we need a separate debounce for each rotary encoder? I think we do. Yeah, we should. Let's do that, because you might have your hand on two of the encoders, and just because you debounce one shouldn't debounce the other. They should be totally independent. So let's rethink this. Encoder 1 debounce So we'll need 4 of these. 1, 2, 3, 4. And the timer increments them all equally, but they might be reset independently. And we'll just reset the state of all 4 down here. Okie dokie. Okay, now I'm getting the feeling we're going to need to refactor this a fair bit to make this a lot simpler. Otherwise, we're going to have a lot of duplicated code. And I'm already thinking, well, do we need 4 individual debounce timers, or do we need an array? Because that'll set us up in a mode where we can use reusable code and say, you know, the interrupt fired and it is encoder 3. Yeah, go with me on this. I'm actually, so going back to single variable, we're going to just do this a little bit differently. This is actually going to can I do this? I don't know if I can actually. It looks like I can. So we're going to increment each of the values within the array of debounce integers, and then can we actually just set the initialization to be 0, 0, 0, 0 like that? Of course we can, or at least it looks like we can. Let's try and build it and see if we really can or not. Aha, no, we cannot. Expected expression. Okay, it didn't love us trying to do that. That's a shame. So we just have to go debounce 0 equals 0. There we go. So that's resetting the debounce timer. Last piece of this puzzle is we need our encoder init to actually be called by our main. Otherwise, there's no point in writing it. Let's do it here. Let's say we're going to initialize encoders. And in order for it to find that, we need to include encoder.h. Okie dokie. Now, if we can build this successfully, yep, we can. Let's just make sure that we are seeing our ISR clock running. I'm going to set a breakpoint just on the interrupt service routine just to make sure we are actually getting that called regularly by the timer. And let's upload our code and debug it. Let's see what happens. There we go. We're straight away in the timer, and the call stack should reveal that it's come from an interrupt. Where is the call stack? Call stack. Oh. CPIC memory views. Okay. What does that? What's that mean? Well, that's very unhelpful. Software call stack is not supported. Defaulting to line at current PC. Hardware stack is supported. CPIC memory views. Well, where? Why can't you give me pick memory views? What does that mean? Pick memory views. View. Target memory views. Program memory. It really doesn't help, but anyway, doesn't matter. Main thing is our encoder clock, our clock interrupt service routine is getting called over and over again, which is perfect. That's really good. Because now we should be able to get a callback when we actually turn one of the knobs. Haha. So, where are we? To do that, we know we've already enabled the interrupts. And this is the CLC here, and it's going to have the same sort of thing. It's got a CLC1 ISR. We need to put some code in there though. Now, how best to do this? How best to do this? Let's say we're going to call out to our own code. We're going to call out to the code in the other file saying encoder CLC ISR, but we're going to pass in an index to which encoder this belongs to. So this is CLC1, so it belongs to the first encoder. And I'm also going to pass in just a single bit to say whether we think this is the clockwise interrupt or the counterclockwise interrupt. Because remember how this works is the gate array that we've got configured within these custom logic cells, kind of like a little FPGA, should result such that if you're turning the knob one way, one interrupt fires, one CLC will see it, versus if you turn it the other way, the other CLC sees it. That's the way we get different code running, whether we're turning clockwise or counterclockwise. That's like the whole reason we do this. So I'm going to pass 0 and 0 to this, whereas in CLC2, I'm going to pass 0 and 1. So that's basically saying if CLC1 fires, it's encoder 0, but it's going direction 0. If CLC2 fires, it's encoder 0 still, but this time it's direction of 1. Now, calling a method that doesn't exist, so let's fix that. Include encoder.h. Do this also in CLC1. Cat's being very weird. Cat's always weird though. I mean, seriously. Void. So what did we call it? Encoder CLC ISR. We get an integer that indicates the encoder, and another integer that indicates direction. And we could use a smaller value there if we wanted to, but let's just keep it real simple for now. So we'll put this up in the header so it's usable via our other code. Why does that not like direction? Is that a reserved keyword? Oh, because you put a comma over there where there can't be a comma. I didn't think direction was a reserved keyword. There we go. Okay, so what have we got wrong now? Encoder.h not found. Ew. Well, that'll be because it's actually, from the CLC's perspective, it's actually ... slash, I think. Let's try to build that. Yep, one less error, so do the same in this file. Build it up. There we go, build successful. Right, so this is cool. That means, and this is like, now we're really getting somewhere, we should see this method called when our encoder is moving either way, right? And we should be able to do different things based on that direction. Now, what should we do? Well, the first thing we got to do is think about how are we going to track the delta. So each of these rotary encoders, basically at any point in time, we need to say, since you last read the value, it has moved up or down based on being turned clockwise or counterclockwise. So I'm going to spec out a similar array of, let's call it encoder value. Oh God. The cat's gone and locked himself in the bathroom. He does this to get attention because he goes into the bathroom, shuts the door behind himself, and then meows like a crazy thing from there. He's like, "Oh, it's dark, and I can't get out. Human, help!" Ginger cats are a special breed. Very, very special. Special in a very special sense. Now, on initialization, let's also zero these all out. Oops, one too many. Okay, so let's debounce first. What are we going to say? What's our debounce threshold? Let's define debounce minimum is 5. We want to see 5 ticks on our encoder clock, so 5 milliseconds elapsed before we debounce. The other thing now, in order this doesn't mean we ignore a value coming in, it means we ignore a change in direction. So we'll need to track one extra bit of state, which is not only do we need to know the current value of the encoder, we need to know 8, let's go uint 8t, we need to know encoder direction. Now, what should we do here? We don't want to necessarily initialize. I guess it doesn't really matter. No, it doesn't matter. Hang on, folks. I gotta go let the cat out of the bathroom. I can hear him wailing and crying because he's locked himself in the bathroom. Back in a second. I let him out and then he expects to be fed. He's got a few screws loose, that cat. So we need to track the direction. That's where we were. And we should initialize these also. Because what we're essentially going to say is if the encoder direction for the encoder that we are referring to here, if the direction, that is the direction we last saw it moving, does not equal direction, so we're thinking we've changed direction here, but we want to debounce that, and the debounce value for this encoder, you know what, I'm going to change this to enc, because that's just going to get too long, and direction can be just dir. So if the encoder direction, the last direction we saw, does not equal a direction that's just been reported, and the debounce value for that encoder, as in the last time we saw, the last time we saw a meaningful value from this, is less than the debounce minimum, then we simply bug out. We just say, not trusting that. That looks like noise. Otherwise, I mean, what's really important to make this work is that we've got to now reset the debounce value and say, well, look, okay, we're going to handle this value. So start the debounce timer back to 0, because this we're treating this as meaningful. And what we basically want to say is, if direction equals 0, then let's treat 0 as counterclockwise. Then take the encoder value for this encoder and decrement it. Otherwise, if the direction's 1, let's treat that as clockwise. And you know what? I can see a nicer way to do this. Let's treat direction as a signed integer. In this way, 0 is a nicer way to do this. We're going to treat incoming direction as a signed integer. And that allows us to be really crafty here and just say, if we're going to treat this as a meaningful change, we'll just do encoder value for this encoder plus equals, so basically add the direction. So if the direction is -1, that's going to automatically decrement it. If the direction is 1, it's going to increment it. Isn't that nice? So that was a real simple way to do that. And I think, oh my god, I just heard another door shut. Is this cat locked himself in the other room? No, okay. Oh boy. Get a cat, they said. He's an awesome cat though, don't get me wrong. He's the sweetest, most cuddly cat. But he's just, sometimes he just gets a little bit wired. So I think we're pretty much done here, right? Each time the CLC fires, it tells us which encoder we're talking about, as well as which direction we're moving in. The direction is either -1 for counterclockwise, so decrement, or 1 for clockwise, increment. And then we say, we handle the debounce, we say if the direction of this encoder does not equal the direction that's been reported, and the debounce is less than the minimum debounce for this. So admittedly, there is like an initial condition here where we would ignore a legitimate first change for 5 milliseconds, but I think we're okay with that. I mean, we could add an extra condition in there and just say, look, if it's 0, allow it through, but we don't need to worry about that. An initial startup debounce at 5 milliseconds is totally tolerable. So if the direction doesn't match and the debounce is too low, return, ignore this value. Otherwise, reset the debounce to 0 and accept the change. I'm going to do it this way around just so it makes a bit more logical sense to me in my head. So act upon the change, then reset the debounce. And this feels very simple, but that should really be it. And that is a giant freight train going by outside. Let's create a little function that gives us back... Jeez Louise. That's a big freight train. Let's create a little function that gives us back encoder values. Alright, so this way a function can, and you know what, we should do this a little bit differently. We should, yeah, I don't think that's gonna work. But we can do it as a pointer. We just need a little function to give back the values. Let's call it get values. And this will return enc value. That's not going to work because I don't think it's going to like the fact that we're predetermining the size of this. So we're going to do this differently because an array is just a pointer. That's the beautiful thing about C. And that totally works. We can say that you call this function and you get a pointer back to an 8int t. In fact, what that pointer will be is a pointer to the first integer in that array, and then we can just use pointer arithmetic to find the others. It's a beautiful thing. Let's build this. We are really close to having the big brain on this board, the STM32 microprocessor being able to read the values of the rotary encoders. Then we're off to the races, right? Then we can determine the position of the knobs, we can affect the control voltages. Hell, we could even get this synthesizer to actually make some noise. That would be cool to do before I go back to work. Conflicting types, yep, that's true. You got me. We did change our definition on this. So let's replace that. And while we're here, let's also add in the get values command. Like that. Build it up, buttercup, help make them strong. What's this? Direct function call made with an incomplete prototype. Encoder init, I2C init. Well, I wonder why. Oh. Does it want a void in there? It does. Okay. Yeah, because these take no parameters, we'll just put a void in there so it doesn't think that we've got an incomplete prototype. It's just a little quirk of C. C quirk. Quirky C. Okay. Wow, that took a long time to build. Encoder get values is never called. Encoder.c. Why has it got an underbar? It's added it in itself. Interesting. Yes, it's never called, but it will be really soon. So don't hassle me. Let's fix that now. Where's it going to be called? It's going to be called in our I2C, and this is getting really awesome here. We can now flesh out our transmit routine here. So switch TX index. So which byte have we been asked for? Remembering back to our documentation. Where is our documentation? Our documentation that we wrote says when we're transmitting data, the first 4 bytes should be the rotary encoder values, the deltas. So this is super simple. We can just say case 0, case 1, case 2, case 3. If it's any of those values in the TX index, set the outgoing buffer, basically the registers that will then transmit this on the wire, to be equal to, and this is, you know what, I think we might do this a little bit different. Remembering we're in a interrupt service routine, speed is key. let's not have a function that calls these, that returns these values. You have it as a static inline, but then we're still copying a pointer. We don't need to do that. Let's just expose this. So we're going to encoder.h, and we're exposing the encoder value, which means over in the I2C function, this just gets ridiculously simple. We've simply got to put in the buffer, the register that's about to go out on the wire, the current value for that encoder, which will actually be relative to the TX index, because first byte is encoder 0, second byte is encoder 1. I love how simple that is. And like, that's it. That's it. That means that, you know, assuming this builds, okay, we're close. Extraneous closing brace. Yeah, I thought I saw something weird in there. Yeah. Okay. Undeclared value. Enc value, because it's going to need include encoder.h. Build this. Now, we got a warning there. Warning: implicit conversion changes signedness. Ah. So, and we're about to do the camera's about to switch over its battery automatically, so if you lose me for a second, don't worry, I'll be back. Now, the buffer that goes out on the wire is just an unsigned 8-bit, right? Unsigned 8-bit integer. It's just 8 bits, right? So it treats it as the simplest unsigned integer. We're actually transmitting a signed integer, but as unsigned. We don't want to change that value, and this wouldn't change the value, but I'm just going to explicitly cast it and say, I know this value here. God damn, another freight train! I know this value in here is a signed integer because we want, you know, the positive and negative, you know, has the user incremented or decremented this value. But I know I'm sending it out as just 8 unsigned bits, so this should just suppress that warning without causing any problems. It's the same bits on the wire. Hey, that's built, except we're getting a warning about an incomplete prototype in here. Yep, so add the void in there. Build this up. Nice. Nice. Oh, this is really cool. So we're ready to start debugging this. And the first thing I want to do is, I guess let's go to our encoder and just see if our interrupt service handler service routine is called, right? If I turn the right knob on this board, does that breakpoint fire? And the challenge will be knowing which is the right one to turn, because there's 40 on there, but only one is actually enabled at the moment through code. So I think I know which one it is. So it's running. Let's see if this breakpoint fires. Pretty sure it's this knob here. Yes! It is! And it fired! And the variables are telling me that it is encoder 0, it is direction 0, so that's interesting. So turning it clockwise produced a direction of 0. And what are we going to do? We've decided to trust it. Oh wait, we need to fix our code here to do the direction differently. Remember? If it's CLC2, we have a positive direction, but this can't be a 0, this has to be -1. Remember, because direction is essentially saying, how should we process this? What should we do? Should we increment or decrement? So let's rerun this. Well, that was pretty cool. Wow, today is like the day of things working. Knocking on the wood again. The cat's not working, I'll tell you that much. Cat.exe over here is definitely struggling. It's gonna be morning tea time soon, I think. Oh, I've got to go back to work tomorrow. Now, don't get me wrong, I enjoy my job. I like my job. I like the people I work with. Most of them. But I just really enjoyed the last week of being able to do this all the time. Okay, so turning it clockwise again. And we got a direction of... we got a direction of FF, which if we display that as an integer, it's -1. Oh, this is so cool. So that's interesting. So we need to just flip that around because we're getting, I kind of want clockwise to be positive. Now turning it back the other direction. Breakpoint fires again. And this time we have a direction of 1, which is exactly what we'd expect. And what do we do here? We skipped over the debounce and we handled it beautifully. And our encoder values are now... Oh, this is so cool. Let's turn the breakpoint off and just spin this knob around a bit. And now put the breakpoint back on. Oh, I think I turned the wrong one. Oh, now I can't get the breakpoint to fire. That's funny. Oh, no, it has fired. It's... Oh, hang on. Sorry, confused myself. Turn the breakpoint off. Let the code run again. Now I just want to turn this knob a bit. And then turn this breakpoint on. And I want to see, have we actually tracked multiple changes? Okay, because now our array here of values, our enc value, should show some interesting values. And look, it does, right? If we, this is awesome. If I change this formatting here to be display as decimal, it's at -20. So it's registered that by turning that knob, we've essentially gone, we should increment whatever value that knob is controlling by 20. I've moved it 20. Arbitrary number, but that's what I've done. I've moved it 20. This works. This works. And we'll fiddle around with, you know, the debounce timer. We can deal with it. We can fine tune that later once we actually start interacting with the instrument and feeling like it's, you know, a bit finicky or a bit touchy on the dials. Last bit in this, we need an encode. Oh, well, we need a method that resets the encoder values, right? Because that's the contract. Once these values have been read, we zero them. So void encoder reset value. And what that's going to do is actually this. So we'll actually take this as an opportunity to call our own function, encoder reset values. Now we need to expose this method externally and make sure that each time on the I2C bus that we actually read any of our values. Oh. Here's a gotcha. No, we should do this differently. Because it's an incremental process. You don't read all 4 values at once and then reset them at once. You read the byte, reset that value, read the byte, reset that value. Okay, so sorry. Backtrack. Take that. Resetting them there is just fine. It's lost its formatting somehow. Okay. Kill that off. We don't need that function at all, actually. And instead, what we'll do is when the I2C method reads the value into the buffer, it's set that in the register at that point in time, and then we can clear the value ourselves. We can now say enc value for this TX index, so for this encoder, equals 0, and that's our reset. Cool, easy peasy. Okay. What else do we need to do? We're now at a point where the STM32 microprocessor should be able to read the encoder values. Okay, well let's go for completeness. Or actually, I think like I said, let's go for completeness first. We need to put this call to the encoder in each of our CLC files here. So first of all, let's just add the header into each of them. So we can do this as a neat copy and paste. And you know what? Before we do, I actually want to see, is that going to mess with MCC? If it generates the code, is it going to complain to this? No, good, okay. Sometimes it gets a bit territorial, and it's like, well, you added this into my file that I created, and I don't agree with it, so get it out, or I can't produce the code for you. So it's like, okay, why don't you go pee in the corner as well? So adding this header into each file, and then make the call. Now we're going to have to be careful with this because it's going to be different each time. So CLC3 should be the same as 1. So let's just get our orientation right. So the odds are -1. Now this is an odd, so it's -1. This is an even CLC cell number, so it's positive. This is an odd CLC number, so it's negative, right? This is just basically doing the clockwise versus counterclockwise. Oh, wait. We also, of course, need to say this is encoder 1 for cells 3 and 4. This is encoder 2 for cells 5 and 6. And this will be encoder 3. And it's the counterclockwise interrupt. And this will be the clockwise interrupt. So, okay, now do we do this after the bit? Yeah, so clear the flag, call our code, 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 clear the flag and call our code, and clear the flag and call our code. Awesome! Now we're all wired up to all 4 rotary encoders on this board. Sweet. And it's built successfully with no warnings that are ours. Awesome. We're not done yet though, because what we don't want to do... Oh, my yawn coming. Oh, must be time for another coffee. I think it is. What we don't want to have to do is we don't want to have to... Oh, hang on. Hang on just one sec, folks. Just coordinating plans for the kidlet. Okay, I'm back. All right, so now our encoders are tracking their state. They should be tracking their deltas. All's good. All's well with the world. But we ain't done yet. We are not done yet. because now you know the big brain, the STM32 microprocessor can ask the little brains, what's your state of all your encoders, and it'll dutifully answer them. But we don't want it to have to keep asking them, right? Because that's really inefficient. Otherwise, because the chip's then got to sit there constantly going, what about now? 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 What we want is the ability for the little chip, the programmable IC, the PIC. We want the PIC to have its ability to put its hand up and say, something's changed. And that's an interrupt, right? That's a hardware interrupt line. And we included support for that in the schematic. If you look at the way these all hook up, they've got a left I2C, so they've got an I2C serial clock line and a serial data line, and an interrupt pin on 25. Pin 25 RB4 is the interrupt, which means here, if we look here, RB4 I2C interrupt. So this is a pin that essentially the main processor is watching at all times to see if that changes state. I know I've got to go and ask some questions. It doesn't know what's changed, it just knows something's changed, and it should go and do the rounds and say, oh, okay, what's happening here then? And it's a little more complex than that because we've got a mux in the middle. So first of all, the interrupt line drops low, and then the mux says, okay, channel 4 has an interrupt. Hey processor, you need to ask some questions of the devices on channel 4 on this mux, right? So it's a bit of a handoff process. It's not as simple as a direct line to the microprocessor like I just kind of made out. So let's deal with that. How will we do that? Well, for starters, let's make sure that pin's configured properly. So it's pin, what do we say, RB4? RB4. Let's go to the pin module. Pin RB4 is defined as I2C interrupt. Now we should start high. It's an analog, it's an output, and it is an open drain. So it never sources current, it just sinks current when it drops. But we should start high because we don't want these things to immediately go, oh, hands up. It's like, no, hold on a second. You need to wait. So it's not until we see something that we should actually drop the interrupt low. And I just want to make sure that these are active low interrupts, aren't they? Let's just double check our spec. Look at the mux first, which is a PCA 9544A. One interrupt. Yeah, 4 active low input. Yeah, okay. So it's high, everything's good. When it drops low, well, of course it's gonna be that way. Yeah, sorry. Right, so we're good. So the last thing we need to do here is if we look at the code that gets created for our pins, there's going to be a function in here for setting that I2C interrupt to low. Now, where is it? I2C interrupt. It's not there. That's odd. I see it in pinmanager.h, but not in pinmanager.c. Weird. Let's generate our code. This pin already existed, so what's going on here? Oh, right. It's look, it's how it does these. It does them as defines that look like functions, and they are. But they're actually a do-while loop, which is quirky, but okay. I guess it's all for performance, so it's inline code. But basically we have a method here that says I2C interrupt set high, set low. And remembering that when we set low, that's basically our way of saying we're pulling the interrupt line down to say, excuse me. I need more sleep. It's our way of saying, excuse me, I need some help. And so we would do that in the encoder method, encoder code here, right? When we change our value and we reset our debounce, we should also pull the interrupt low. Let's say pull interrupt okay. And I think the other thing we need to do is, you don't want the interrupt to then stay low all the time. You've got to set that back when we think we've gotten the attention we need, right? This is microchip attention seeking. So we've pulled it low when something has changed. But then when we get the attention we seek, as in we see that we're getting read to or written from, then I think we should reset our interrupt here, right? Whenever we are called because the master wants data from us, we should set our interrupt back high. Okay. So something changes in the encoders, we pull it down and say, I want your attention, microchip, or CPU. And then the CPU says, okay, well, tell me what's your data. And we release it and say, okay, thank you. It's a bit weird that I guess it's fine. We're releasing the interrupt once it first starts talking to us, and I think that's fine. Okay. So, yeah, that should be it. Now, for something really cool, when we pull our interrupt low on the PIC, the MUX, the I2C switch that sits between our PIC and our STM32 microprocessor, it should pull its own interrupt low so that the CPU sees it, right? And we ought to be able to add code in now to catch that, right? So we should see a breakpoint. We should get to the point soon where we should see a breakpoint fire within our main CPU because we've adjusted one of the rotary encoders. Let's try and get to this point. So, I think I've already configured the pins by the look of it. I2C1 interrupt pin, and do we have I2C2 interrupt pin? Doesn't look like I have done that yet, but that's okay. We know we're on the left bus with this, aren't we? We're on the left bus? Yes, we are. Which is I2C1. So if I've already got code, what's it doing? I2C1 interrupt. Let's search for that. Okay, we've got to sort of context switch now back into the main CPU land and see what have we added. Interrupt handler. So these should be all the interrupt handlers. Here we go. XDI95. Okay, that's right. So we've got to work out which interrupt is this defined as. So our interrupt line that comes from the switch is defined as external interrupt 5. Okay, so it is that. So where were we? Back in here. Oh, why does that file reopen every time? Yeah, nice. So this is like the code to run while the interrupt's 0, and then this resets our state, and this is after we've reset the state. So a breakpoint here ought to fire whenever we now touch one of the rotary encoders. Holy crap, if this all works, we'll be astounded. delighted, but astounded. So let's build the code for the PIC, run it on the PIC. Okay, user program running. Now, just check we don't have any breakpoints. No. Okay, so it's off merrily doing its own thing now. But let's see what this end is doing. Now, interestingly, by touching the rotary encoders like that, I will have pulled the interrupt line low. So let's see if we now run this code. Does it go straight into our interrupt handler? I've got to close that file, I think. Here we go. So, oh, that's interesting. We were not able to talk to the I2C switch. Well, that's all sorts of bad. Why would that be? I need to reset the board. How busy? What does how busy mean again? Okay, well let's not monkey around. Let's just give this a power cycle. There we go. When in doubt, reboot. And now let's rerun our code. Close this file because otherwise it keeps reopening. Let's run this. Okay, well at least we haven't got that error now talking to the mux. So everything should be hunky-dory on that board now. It should be happily talking to the PIC. I'm going to restart the PIC's code. That might cause this to error out while the PIC goes off into being reprogrammed, but let's leave it be for now. Alright, so we're now primed. I'm hoping if I touch one of the control knobs now that we hit this breakpoint on the main processor, and so that means the processor is being made aware that we are changing one of the control values. Oh my, it worked first go. Look at that. We went straight into the interrupt handle that I expected. So from here, now this is awesome because this means that the main processor can go and turn around and say, okay, give me your values. Someone's telling me something changed. Give me all your encoder values and I will go update accordingly. Okay, awesome. I'm going to take a break at this point because we've been going for an hour and a half, and I'm going to get up and stretch my legs and work out what is the next thing we're going to do. It requires a bit of planning, and that's not the kind of stuff we necessarily want to do thinking on our feet, but might be back in a little while. So I'll see you then. Thanks so much for hanging out, and have yourself an awesome